Okay, so kind of like last time, and now all of us are already on, so hopefully a little bit less frenzied. Again, the idea is to sort of provide you with all of these notebooks that should work as a resource for you to keep coming back to. So what we're going to do is we're going to go through just first this one, vesicle, doing degassing paths with, again, that's just H2 and CO2. And then Ari is going to talk about the Volfi model, which includes sulfur. So all the other models include sulfur. And then I think there's a couple of other pieces we want to say.
Yeah, I think Echo will just share sulfur X.
About sulfur X, because that one has a little bit of specialties with it. So we're gonna go through these, but we're gonna kind of launch you off then to keep running the notebooks, and then we can talk about things around and see if people have questions. So degassing paths. So this is an interesting way to really look at model variabilities because it combines a lot of different thermodynamic equations and calculations and assumptions within the model. So we did the saturation pressure before, and already we have differences in what models are calculating for that. And that's the point from which we're going to calculate our degassing paths. Now, I think for most, if not all of these models, you can choose to set it at a different pressure. But oftentimes we have a melt inclusion, we assume it's volatile saturated, and we want to start from that pressure of saturation and degas it from the magma chamber up to the surface. And so now you are getting differences in the solubility coefficients or constants, or we can't decide the best way to call them, but some form of the equation explaining the solubility, the equilibrium between the vapor and the melt. These are different choices. The way that people are translating values, for example, FO2, you're going to see that there's a huge effect of that causing some of the divergence of the sulfur bearing models. And so it's kind of compounding all of these things from getting us from that pressure of saturation to the surface and to what the vapor pressure is, or sorry, the vapor composition is at the surface. And as Ari was just showing, that's a super important way for volcano observatories to monitor volcanoes ongoing and for us to understand what's going on beneath the surface, because as you so eloquently put it, it's the only thing coming out of the volcano before an eruption, which I love. So yeah, but it's not, oh, the seismic energy, sure. I don't know, how much is it attenuated through the air column? Well, all energy has mass. E equals mc squared, my friend. Okay, so let's go ahead and start going through these. Once again, you're going to see this aerothermal engine is not installed. Pro tip, if you see an error, don't know what it is, and it keeps going, ignore it. Python does that a lot. You pip install something and it's like, you shouldn't do this with pip. Too bad, do it anyway. Sudo pip install. So again, we're using the version of 1.2.12. Publishing that with your results is super important. And we're going to be reading in that output file that we created earlier. Once again, if you're having trouble with that now, or you just simply haven't run that notebook yet, go ahead and uncomment this by removing the hash, and then let's see this, and then run that cell again, and it should be the same file unless you've edited that output file. So something I didn't go over because we were short on time last time is again the model options. Now all of the models have a ton of different model options. Slightly simpler in vesicle because we're simply just implementing an existing model. So you can look at the different models that are in vesicle. There's an example of how to do that in the earlier spreadsheet. Here we're using Giacomo-Marciano, but at any time you can go and change that. So when you see here, oops, we're just printing out the sample information. Wow. Oh, there we go. I thought it was 900 million weight percent. So just to show you real quick here, when we're going to do the actual calculation, you'll see something like this, right? When we run, I'm just giving ahead here to show you this, model equals Giacomo-Marciano. Now, if you're running vesicle and you don't specify that, it'll run with magmasat, which again is a special thing that has advanced installation requirements. So we don't have it on this Victor server, but you can change this to anything that this will take. So Dixon, for example, is what you can run with. Yeah, and other than that, a good thing like to always do, and as we're showing in these notebooks, is to examine the data that you're putting in. So yes, you pull on the spreadsheet, but then you might be creating for InvestiCal, for example. So first we're just reading this spreadsheet. Hopefully that looks the way it should. Otherwise it's a different problem. But InvestiCal, we use something called a sample object. So Python is object oriented. A lot of codes are object oriented, means everything is treated like a thing with properties. So our sample has a composition, it might have a temperature, might have a pressure, so it kind of gets saved within that object. And so that means that something could go wrong. Maybe there was a misnamed column or something, and I've written this code badly such that it didn't tell you. And you end up, I would run my own code when I first started making this, and I had like 0% silica. And I was like, why aren't any of these making sense? So just looking at that to see that you're actually getting something that makes sense is a good idea. And we do. So you can see this is just showing you one of the samples. So again, I'm not going to go exhaustively through all of these, so I'll let you do that on your own. But you can go ahead and run these calculations. You can change any of the parameters. You can edit that CSV file and run it through. Then again, knowing that if you're editing that output file, it's going to be different. So you can always go back to the results folder file to match the other calculations. Yeah, and you should be able. Is anyone having issues so far? That stuff not running?
Should we be working ourselves through 2.1, 2.2, and so forth now?
Feel free. Yeah. Feel free to go on if you're ahead. We are going to have Eric come talk about that. And I think Echo's going to say stuff about it. But yeah, feel free to just blow through all this. I'm sort of here to give you this logistical overview. So you should end up with something like this. And then we'll be able to compare all the models at the end and see what that looks like. So do you want to talk about Volfi? Cool. If anyone has issues, just raise your hand and we'll come try to help.
So Volfi, we briefly said before, essentially Volfi has water and CO2, but also sulfur. And that means it has a bunch of other species. So it's got water, CO2, it's got hydrogen, CO, methane, SO2, H2S in the vapor, and then like S2 minus and SO4, 2 minus in the melt, as well as H2S. So there's a whole bunch of new species in Volfi that you don't have in VCal. And because it's got these additional species, we also consider oxygen fugacity. So oxygen fugacity is a measure of how oxidized or reduced the system is. And the reason it's important when we start to have sulfur involved is because sulfur can be S6 plus or S2 minus in the melt. And so you need to know what the FO2 is doing. And so in this notebook, the first cell, it's just loading the packages. But what we can do is, again, yes, we will just say the version number is super important. These cells are all the same in all the notebooks. We're just going to import the data. This cell here is a bit different, or the way you can tell Volfi what model to use is different from how VCal does it. So in VCal, you saw you had that little option that you could change. In Volfi, you can create this models dictionary, and that will tell it like for all the different parts of Volfi what to use. And in Volfi, there's a huge number of different options. So the solubility functions you're going to use, so basically how it's telling it to dissolve water, you can vary the CO2 solubility model. You can also look through all the fugacity coefficients as well and see what models they're using, because Volfi has very few in-house models. It's mainly just drawing on models from the literature to do the calculations. And it is important when you show, and there's a final notebook number 3 that shows you that you should really be specifying every model option you're using when you run these codes, because if I use a different model option to you, I'm going to get different results. And I can't recreate your calculation without that. For Volfi, in the output file, it has all the models you've used. So they are at least recorded, but you should also be telling people that. So that's what this one. And then, we need a set for a degassing calculation. We need an initial composition. So in this case, we're going to say, what is the volatile composition of the melt at PV-sat? And we're assuming there's no vapor present in this case. So it's all in the melt. And so in this case, we're just taking the melt inclusion with the higher CO2. And that's because it's going to plot nicely on our plots. But you could specify this. We need to specify another parameter here. We need to know what the initial oxygen fugacity of the system is. Volfi can take this in a variety of ways. So you could say the Fe3 plus 2 plus, you could say the delta NNO, the S6 plus S total. If you specify too many ways, Volfi's going to pick which one it wants. It'll tell you which one it wants, but it has its own order that it's going to prefer. So if you put lots of different options, you've over-specified FO2, basically. which is in this case what we've done. We've given it FeO and Fe2O3, and we're now going to tell it delta FMQ. And Volfi goes, I'm going to take delta FMQ. So it's going to ignore your FeO, Fe2O3, for instance. So we can specify what this is. And then we create, as we did for VCal, this is our initial composition that we're going to start with. All of these tools have different naming conventions. We don't agree. So that's what this part is. We're just making them all kind of talk to each other. And then we're going to run. So that's that warning where I said you've vented lots of things. I'm using delta FMQ. And now it's just solving. It's not quite as quick as some of the other models. While it's doing this, I'll just say Ekka's going to talk about sulfur-X. We have put in a notebook here for Evo. This is a model by Pip Liggins when she did her PhD. And that's, we won't go through it, but that's another model that has all the same species as Volfi as well. So that's another option you can compare to. And I think Ekka showed in her first presentation, sulfur-X versus Evo result. So it's finished. No, it's not quite finished.
That's so low.
I'm sorry.
Solving chat.
I know.
Wait,
You mean you keep up with the variables?
sorry there.
Can I quickly talk about the tiny number, like why the solving chat?
Oh yeah, so it's actually not trivial to solve these calculations, especially if you're at low water and CO2. Actually getting it to converge in a solution can be quite tricky. And that's because the way, for instance, Volfi solves is it guesses the vapor composition. It guesses 3 species in the vapor, and then it can calculate everything else from that. So you guess 3 species, calculates the amount of vapor composition, and checks for mass balance. And essentially, when you start to have very low concentrations of species in the vapor, it really struggles. So you can get problems where it doesn't solve, unfortunately. And in all these models, there are times when that happens. Low water and low CO2 for Volfi can be a problem, basically. So unfortunately, like I've tried really hard, so most combos do work, but there can be solutions when it doesn't. And then we can just plot, and we're going to compare to the melt inclusion of data. And just to highlight, we all have different output header names. Sorry. So if you change this data frame to the results from sulfur-X, it won't plot because sulfur-X doesn't call water in the melt H2O-T-Ek_weight%. So just to be aware that that's a problem. And so this is what we're getting. So we can see we've got pressure on all these axes. So for VCal, you can only plot the first 3 panels because it only does water and CO2. But with Volfi and the other models, we can start to plot the sulfur-bearing parts. So we've got sulfur in the melts. You can see the Fe3 plus over Fe total ratio of the melt. And I'm comparing it here to what we've calculated from the melt inclusions. And then the final plot is the SO2 over SO2 plus CO2. Now, just to point out, the reason we're getting great agreement between SO2 over that final plot is because that's what Volfi calculated from the melting functions, right? That's not a measurement in the melting function. So Volfi used the same models to calculate the degassing path as it calculated this quantity for the melting function. So we would expect there to be a good agreement because they're using the same models for this. Do you want to quickly talk about sulfur?
The sulfur mass. The melt inclusion show sulfur mass, but only is
Yeah, so in this case, well, the ferrous isn't a measurement. So that's a calculation at delta FMQ. I specified that for each one.
These melting fusions have undergone sulfide growth inside of them after they formed. So it's dragged the sulfur off that degassing line. So yeah.
Okay.
Come and chat to me at lunch if you're curious. But sulfur correlates perfectly with iron in these melting fusions and with copper.
Do you want to?
Yeah, so we can also do the similar calculation for degassing using sulfur-X. So sulfur-X has water, CO2, and then counting sulfur. In the melt is sulfate and sulfide, and in gas it only counts for SO2 and H2S, which is kind of the main gas species. on Earth. So the same we can start, and then it actually takes other inputs, but everything would be like input in the notebook. So it's like a workflow. So we can first just run the cell, import things. And then here it actually reads. So SoftwareX doesn't have a pip install yet. So everything would be, if you go into your folder, you will actually see this SoftwareX main thing. So all the SoftwareX code is actually in this folder. So the workflow is just like you don't have to go into the code itself. You can just run through. So this code, the second cell is basically just to read the directory of this folder. And then we can import data again. It's the same set of data just for comparison. I think we have a separate notebook to compare all the results. And then explore the options. So this is where, so SoftwareX has the in-house model is actually, it calculates software using partition coefficients. So that's what the in-house model, we have to calculate the sulfide and the sulfate partition coefficients. So there are two partition coefficients. And the rest, we actually use other models, for example, for water CO2. So here, so these are where we could choose different things. So for example, for water CO2, for now we have the volatile calc or the Incano-Marciano model. So here we just, here it all has this explanation, like what do you want to choose? And then it also deals with the FO2 change, but then it involves this how sulfur speciation change with iron. So we have a few models there too. So these are all the options, I guess. You can turn off the FO2 track. So I think all the sulfur varying degassing model can track how FO2, magmatic FO2 actually change as sulfur degassing. So here you can actually turn it off or turn it on. So we turn it on. For crystallization, it doesn't really do its own crystallization model. It actually requires you to input maybe like a empirical melt composition change in a separate, inside this SoftwareX folder. It has something called melt composition. But it does count, if you, once you input that change, then it can count the composition change. So we turn it off. And for sulfide, we turn it off too. So these are all the stuff we can change. It also can calculate open versus closed degassing. So 0 would be closed degassing, and you can actually have it open degassing from any pressure. So basically you can input the number. So it all explained here. Oops, what's going on? Can I just? Okay. Oh yeah, good. So we can just run this, just set all this. And then the next cell is also like, you can adjust the degassing steps. So that's what the total, the L is. And then you don't have to run all the steps. You can just if you are not only interested in like the most shallow part, you can actually run maybe, 900 step of that, or you can change the degassing step. So that would actually basically is as a decompression, how big your pressure step is. So we could just run these. And then I think here what we're doing. Oh, this is just reading the melt inclusion. Yeah. So these are reading the melt inclusion. And then we read, so these are just reading all this melt initial composition, because as I think Eric said, it does not we all have like different headers. And then so SoftwareX takes DFMQ as the input of the FO2. And then, oops. So this is just showing what's the melt inclusion we're reading. We're reading the same thing. And then here you can change the temperature. Oh, yeah, you can either change it or we're actually reading from our initial composition here, okay? And then, so all this is just input all the initial into that SoftwareX function in the other folder. So we can just read. And now here's the run. And yeah, so it will give you this initial input just give you kind of a look at, okay, where does the saturation pressure is. So here, SOFRX does not count the sulfur degassing in the first step to actually calculate the saturation pressure. It only uses the water and CO2. And then it will give you what's the first step, what's the vapor saturation, just give an idea, and also the initial ferric iron ratio and sulfate speciation, everything. Yeah, so now it's done. So we are just plotting how the results look like. And then we can, I think the last cell is just to read into the result cell, like for the notebook number 5 to compare all the results.
How much time have we?
So we're actually right on time now.
At the end?
Yes,
Okay, so,
but we could go for another 10 minutes.
oh, well, maybe people over lunch can have a play with these notebooks.
Yeah.
We'll just show the final. So I'm not going to run through Evo. Evo has the same, we've used the same formula for all of them. So they're all running the same composition, etc. But there's also this final one, which is just the comparison notebook. So this is where you can, it's going to read in all the results. And so here it's not actually, this notebook, what's it having? Geez. We didn't run Evo. There we go. Okay, so what we'll do. So we gave you all the answers. So if you uncomment this cell, it's all the answers. Fab, cool. We're also we can just plot the, there we go. There are some parts I haven't run. Oh no, that's fine. Oh, I see, and it skips a cell. Sorry, thank you. Is it going to flow over again? Okay, but we've it had the same problem. We'll just start from here. So yeah, you can now compare all of them for it. I'll just point out, we've given you these as little exercises, but there's actually a notebook that does all of these exercises in one. So you can actually run for a single composition everything and get these outputs.
1 second.
Yes.
So what you'll notice is that that bottom right plot is showing the fluid infusion chemistry against the models, and all of them are under predicting how much sulfur is in the fluid infusion. Now, those of you with eagle eyes, does anyone notice what the percentage of sulfur 6 plus was in Echo's model run at the start? It was 16% iron 3 plus, and it was 1% sulfur 6 plus, whereas Zane's for Kilauea is about 20% sulfur 6 plus. So that's one really nice thing about Echo's model, is you can actually adjust some of those coefficients, and she talks about this a bit in her paper. So if you wanted to, for your homework, you could try changing that sulfur 6 plus model, and you'll see your sulfur degassing much, much earlier. So basically, good homework exercises, go and look at the sulfur 6 plus outputs for this and compare them to your data. And Kayla's paper that she sent around as a preprint talks about this a bit more. Sulfur 6 plus is a super variable output in these models, and it's worth paying attention to. Cool.
Does anyone have any questions? We break for lunch.
So maybe a clarification.
Do you want to use your brain?
Yeah.
I'm told it's not working, but
It is.
Still listening.
Can you clarify the sulfur X? You said that you use a partition coefficient for the sulfur species. Shouldn't that vary with pressure?
Yeah, so
Oh, Mike, if you just switch yours off, Tom.
There is everything.
Tom, can you switch your mic off?
Yeah, so it calculates the speciation change at different each step. It will recalculate and then recalculate the KD, everything. So yeah.
Go, Penny.
Another, clarification question to the sulfur X. What's it using for the ferric ferrous ratio?
If you can turn yours off, Penny.
Yeah.
Are you talking about from ferric ferrous ratio to FO2? Chris Carmichael. Yeah.
There's another question over here somewhere. Oh, John.
Could you say something about the relative performance of the models for basaltic systems versus intermediate arc systems, for example, leading to high silica rhyolite systems?
This is the.
You need to like that.
Okay, so great question. So what I'm gonna be showing at the end of today is the model comparison we've done for basalts. And the reason we've done for basalts is because there's overwhelmingly more data for those. The next best thing would probably be the more rhyolitic systems. The least amount of data we have is in the intermediate systems, which is sort of too bad since those are some of the most important for volcanic hazards. There's also complications, whether or not they're that important, but there's complications with the intermediate magmas because they have different like dissolution mechanisms. So basalts, for example, dissolve carbon as CO3 and rhyolites as CO2. So in the middle, there's some lever there that's controlling that. So to answer your question, we haven't done the thorough look at this, but you can also read Penny Wieser's paper, Vescal Part 2. It's 2021, I think. And she talks a lot about that and kind of points out this issue. And compares some of the models that we had within Vesical and more. Did you do Papale? Some of those?
Only for CO2 and water, not for salt.
Right, yeah, only for CO2 and water. So the point is it's gonna be worse. And this is somewhere that, that's somewhere, I wanna talk a little bit about too, how we can need to target in experimental studies. And this is one of those things for sure. I think we've known about it for a while, but this gives a more tangible look at that.
And actually, the catalyst that we have that's funding this workshop, part of that was to do also experiments on the intermediate system.
Okay, let's break for lunch.